The technician's hands trembled slightly as he lifted the device from its wooden crate. It was heavier than expected, roughly 20 pounds of precision-machined aluminum and optical glass, still bearing faint traces of oil from an American assembly line. Outside the hangar at Recklinlerz Airfield, snow fell across the Mecklenburg countryside on this February morning in 1943, but inside, a circle of German engineers stood in absolute silence, staring at what they had been told was impossible. A fully intact Norden bomb site, serial number visible, pulled from a B-17 that had crashed near Schweinfurt 3 weeks earlier. Hauptmann Werner Batz, chief of the Luftwaffe's bomb site evaluation section, approached the device with the careful reverence of a man handling an artifact from an alien civilization. For 2 years, German intelligence had insisted the American precision bombing campaign was propaganda, that the daylight raids were suicide missions producing nothing but scattered craters and dead air crews. For 2 years, Batz had written reports explaining why the Americans couldn't possibly achieve the accuracy they claimed. Now, holding the physical evidence of his incorrectness, he felt the first stirrings of a realization that would metastasize into something close to despair over the following weeks. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The Norden bomb site had acquired an almost mythological status by early 1943. American newspapers called it the secret weapon that could drop a bomb into a pickle barrel from 20,000 feet. German propaganda dismissed these claims as typical American exaggeration, the boastfulness of a nation that understood marketing better than warfare. But the men at Recklinlerz were engineers, not propagandists, and they understood that the pattern of destruction across German industrial centers suggested something far more sophisticated than the crude area bombing techniques employed by the RAF at night. The device before them represented the culmination of nearly 15 years of American engineering effort. Designed by Carl Norden, a Dutch immigrant who had become obsessed with the problem of accurate high-altitude bombing, the Mark 15 bomb site was an analog computer of staggering complexity. It contained approximately 2,000 moving parts, gears, gyroscopes, mirrors, and motors that worked in concert to solve a problem that had bedeviled military planners since the first aircraft had dropped the first bomb. How do you hit a target from 4 miles up, traveling at 200 miles per hour, with a bomb that will be affected by wind, altitude, temperature, and the Earth's rotation during its 40-second fall? German bomb site technology had followed a different path. The Luftfernrohr 7, standard equipment in Luftwaffe bombers since the Spanish Civil War, was an elegant device in its own right. Designed by Carl Zeiss, it used a simple mechanical computer to calculate the bomb release point based on altitude, airspeed, and target angle. German pilots had used it effectively in the early war years, particularly during the precision attacks on Warsaw and Rotterdam. But the Luftfernrohr 7 was designed for a different kind of war, low-altitude attacks, often below 5,000 feet, where the bomber crew could visually identify targets and adjust their approach in real time. It was a tool for tactical bombing, for supporting ground forces, for terrorizing cities already under siege. The Norden bomb site was built for a different purpose entirely: strategic bombing from altitudes where anti-aircraft fire was less effective, where fighter interception was more difficult, where the bomber could operate in relative safety while destroying the industrial capacity that fed enemy armies. This distinction, Batz was beginning to understand, represented not just a technological gap, but a fundamental difference in how Germany and America conceived of air power itself. The story of how this particular bomb site arrived at Recklinlerz involved a combination of German determination and American miscalculation. On January 14, 1943, A formation of 64 B-17 flying fortresses from the 306th Bomb Group had attacked the ball-bearing factories at Schweinfurt, deep in southern Germany. The raid was part of the 8th Air Force's broader campaign to cripple German industry by targeting what American planners called panacea targets, facilities whose destruction would cascade throughout the entire German war economy. Ball bearings, used in everything from aircraft engines to tank transmissions, seemed like the perfect choke point. The B-17 designated Liberty Lady, serial number 42373, had been hit by flak over the target. The damage wasn't immediately catastrophic, but hydraulic fluid was streaming from the number 3 engine, and the aircraft began losing altitude. The pilot, Lieutenant Robert Harmon, ordered his crew to prepare for a forced landing, hoping to reach Switzerland and internment rather than capture. They almost made it. The aircraft came down in a farmer's field 37 miles from the Swiss border, skidding through frozen earth before coming to rest against a line of bare oak trees. German troops arrived within 20 minutes. Standard procedure for captured American aircraft called for immediate destruction of sensitive equipment, and the bombardier, Lieutenant James Kellerman, had attempted to comply. He had smashed the optical components with the butt of his service pistol and poured coffee from his thermos into the mechanical housing, hoping to corrode the gears. But the Norden bomb site was robustly constructed, and Kellerman, facing German soldiers with rifles raised, had perhaps 30 seconds to destroy a device that represented 2,000 hours of precision machining. He managed to crack one of the external lenses and jam the gyroscope mechanism with a screwdriver, but the core computing assembly remained intact. The bomb site was immediately recognized as the intelligence prize of the highest order. It was transported first to Munich, where Luftwaffe intelligence photographed every component, then to Berlin, where Admiral Wilhelm Canaris, head of the Abwehr, personally examined it before authorizing its transfer to Rechlin-Laerz for technical evaluation. The entire journey took 5 weeks, slowed by Allied air raids that disrupted rail transport and by the paranoia of German security services who insisted on multiple authentication checks to ensure the device wasn't a plant. A deliberately sacrificed decoy designed to mislead German engineers about American capabilities. Now, in the cold hangar at Rechlin-Laerz, Beatz and his team began the painstaking work of disassembly and analysis. They worked under intense pressure. General Hans Jeschonek, chief of the Luftwaffe General Staff, had demanded answers within 2 weeks. How accurate was it? Could it be countered? Could it be copied? The questions arrived daily from Berlin, each one edged with urgency that bordered on panic. The Americans were expanding their bomber forces at a rate that German intelligence found difficult to believe. Current estimates suggested the 8th Air Force would field over 1,000 heavy bombers by summer. If those bombers could hit their targets with the precision that recent raid patterns suggested, the implications for German industrial production were catastrophic. The first surprise came during disassembly. The Norden bomb site was not, as German engineers had assumed, a simple optical rangefinder with basic mechanical computation. It was a stabilized platform incorporating a gyroscope-controlled autopilot that could actually fly the aircraft during the bombing run. The bombardier, looking through the sight, could input target data, and the device would automatically adjust the aircraft's heading and speed to achieve the optimal release point. The pilot, during those critical 30 seconds before bomb release, was essentially a passenger. The machine was flying the plane. This revelation disturbed the German engineers at a fundamental level. Luftwaffe doctrine emphasized pilot skill and initiative. The idea of surrendering control to a machine, even temporarily, contradicted core assumptions about aerial combat. But from an engineering perspective, it was brilliant. Human pilots, no matter how skilled, introduced variables. Slight corrections, muscle tension, fatigue. The Norden eliminated these variables. During the bombing run, the B-17 became a ballistic platform as stable and predictable as an artillery piece. The second surprise emerged during the analysis of the optical system. The Norden used a telescopic sight with magnification capabilities far exceeding anything in German service. At 20,000 feet, a bombardier could identify individual buildings, could distinguish between a factory and a warehouse, could place crosshairs on a specific section of a roof. The Luftfernrohr 7, by contrast, was designed for target areas measured in city blocks. Precision in the German system meant hitting the right neighborhood. Precision in the American system meant hitting the right building. But the true genius of the Norden revealed itself in the computing mechanism. Carved into the device's housing were the equations it solved, continuous differential equations accounting for wind drift, altitude pressure differentials, temperature gradients, and even the Coriolis effect of Earth's rotation. The bomb sight was recalculating the bomb's trajectory 30 times per second, adjusting for variables that German bomb sights treated as negligible constants. It wasn't just more accurate than German technology. It was operating at a different order of mathematical sophistication. Botz spent 3 days simply trying to understand the mechanical computer's logic. He was a capable engineer, trained at the Technical University of Berlin, with a decade of experience in aviation systems. But the Norden's design philosophy was alien to him. German engineering typically emphasized elegant simplicity, the minimum number of parts necessary to achieve a function. The Norden was maximalist, 2,000 parts working in concert, with redundancies and fail-safes built into every subsystem. It was the product of a nation with such vast manufacturing capacity that complexity was no barrier, where precision machining was so standardized that microscopic tolerances could be achieved in mass production. This realization led Botz to a conclusion that he documented in a memo dated February 23, 1943, a memo that would be classified as secret and would remain buried in Luftwaffe archives until discovered by historians in the 1980s. The problem, Botz wrote, was not simply that the Americans had built a better bomb sight. The problem was that the Americans could afford to build a better bomb sight. Each Norden unit cost approximately $8,000 to manufacture, roughly the same cost as an entire German fighter aircraft. The B-17s were arriving over Germany equipped with devices that cost as much as the fighters trying to shoot them down. Germany, Botz calculated, could not replicate the Norden even if given complete manufacturing specifications. The machine tolerances required components machined to accuracies of 1/10,000th of an inch. German industry could achieve these tolerances in laboratory settings, but not in mass production. The gears alone would require specialized equipment that Germany did not possess, and could not build without diverting resources from tank and aircraft production. And even if Germany somehow manufactured 1,000 Norden bomb sights, the Luftwaffe had no heavy bomber fleet to mount them in. The strategic bombing arm had been effectively disbanded in 1942, its resources redirected to tactical aircraft supporting the Eastern Front. The engineers at Rechlin-Larz conducted actual bombing tests in March of 1943, mounting the captured Norden in a Heinkel He-111 bomber and attempting to replicate the conditions of an American raid. The results were simultaneously impressive and demoralizing. In optimal conditions, with no enemy action, clear visibility, and multiple practice runs over the same target, the Norden achieved accuracy within 50 yards from 20,000 feet. This was approximately 3 times more accurate than the Luftfernrohr 7 could manage under similar conditions. But the tests also revealed the Norden's limitations. It required clear visibility. Clouds or smoke obscured the target and made the sight useless. It required stable air. Turbulence disrupted the gyroscope stabilization. Most critically, it required uninterrupted bombing runs lasting 30 to 45 seconds, during which the aircraft maintained steady altitude and heading. In combat conditions, with fighters attacking and flak bursting, these requirements seemed impossibly demanding. This is where German analysis made its critical error. Botz and his team concluded that while the Norden was technologically impressive, combat conditions would reduce its effectiveness to levels comparable with German systems. They were correct in their technical assessment, but failed to account for the strategic context in which the Americans operated. The B-17 formations were not individual bombers trying to survive. They were flying fortresses designed specifically to maintain steady formation flight under fire. The entire American tactical system, from the aircraft design to the formation patterns to the defensive armament, was built around enabling those critical 30 seconds when the Norden needed stability to work its mathematical magic. The psychological impact of the Norden evaluation on the Rechlin-Laerts engineers was profound and, in many cases, permanent. These were men who had been raised in a culture that prided itself on technical superiority, who had been taught that German engineering represented the pinnacle of human achievement. The precision optical instruments of Zeiss, the chemical innovations of IG Farben, the automotive engineering of Mercedes and BMW. These were not just products, but proof of cultural superiority, evidence that German Kultur produced better results than American commercialism or British pragmatism. The Norden bomb sight challenged this worldview at a fundamental level. Here was an American device, produced in quantity by workers who likely had less formal education than their German counterparts, that exceeded German capabilities in every measurable dimension. It wasn't marginally better. It was categorically superior, operating at a level of sophistication that German industry could not match even if given unlimited time and resources. Botz's final report, submitted to Luftwaffe Command in April of 1943, was a masterpiece of diplomatic language, carefully phrased to avoid defeatism while conveying the essential truth. The Norden bomb sight, he wrote, represented a significant technical achievement reflecting the Americans' characteristic approach of applying maximum resources to engineering problems. He recommended against attempting to copy the device, noting that German engineering principles emphasize efficiency and elegant simplicity, which has served our forces well in combat conditions. He suggested instead that Luftwaffe doctrine focus on disrupting American formations before the bombing run could be completed, exploiting the Norden's need for stable flight during the critical release sequence. What Botz could not say, what would have been dangerous to articulate even in a classified report, was that the Norden bomb sight had revealed something far more threatening than a tactical disadvantage. It had revealed the scale of American industrial capacity and the sophistication of American mass production. A nation that could build thousands of devices this complex, that could equip hundreds of bombers with $8,000 bomb sights, that could afford to lose dozens of these aircraft in a single raid and return the next week with the losses replaced, was operating at a level of material abundance that Germany could not hope to match. The engineers at Rechlin-Laerts had test-fired a captured American bomb sight and discovered, with the cold clarity that only mathematics can provide, that Germany was losing a war it had assumed it would win. The device in the hangar was not just a piece of technology. It was evidence of an economic and industrial reality that German propaganda had insisted did not exist. The Americans were not bluffing about their productive capacity. The pickle-barrel claims were not exaggeration. The daylight bombing campaign was not a desperate gamble, but a systematic application of overwhelming material advantage. In the months following the Norden evaluation, several of the Rechlin-Laerts engineers requested transfers to other duties.
Two retired on medical grounds, citing stress-related ailments. Botts himself remained at his post until late 1944, continuing to evaluate captured Allied technology and writing increasingly pessimistic reports that were increasingly ignored by Luftwaffe command. His final assessment, written in November of 1944 as American and British forces closed in from both east and west, noted that German engineers had consistently underestimated not just Allied technical capabilities, but the industrial systems that made such capabilities possible. The irony of the Norden evaluation was that German intelligence had been partially correct in their initial skepticism. The bomb sight was not quite as accurate in combat as American publicity claimed. The pickle barrel boasts were indeed propaganda, marketing language designed to build public support for the daylight bombing campaign. In actual combat conditions with clouds, smoke, flak, and fighters disrupting bombing runs, the circular error. Probable of American bombs averaged closer to 300 yards than the 50 yards achieved in optimal testing. But 300 yards was still extraordinarily precise compared to area bombing. It was accurate enough to destroy specific factory buildings while leaving surrounding neighborhoods relatively intact. It was accurate enough to hit rail yards, oil refineries, and power stations with predictable consistency. Most importantly, it was accurate enough to make strategic bombing feasible, to make the devastation of German industrial capacity a matter of time and repetition rather than luck. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The captured Norden bomb site remained at Recklinlerz until January of 1945, when the facility was evacuated ahead of advancing Soviet forces. In the chaos of the retreat, most equipment was either destroyed or fell into Soviet hands. The fate of this particular device is unknown. It may have been captured by the Red Army and shipped to Moscow for evaluation, or it may have been destroyed by German engineers following protocol. The paper trail disappears in the final months of the war, lost in the collapse of German record-keeping as the Reich disintegrated. But the knowledge it provided, the psychological impact of its evaluation, persisted in the memories of the men who examined it. In post-war interviews, several Recklinlerz veterans recalled the Norden assessment as a turning point in their understanding of the war. Lieutenant Colonel Heinrich Büchner, who had assisted in the disassembly, told an American historian in 1968 that "We knew we were losing after Stalingrad, but examining the Norden was when we understood why we were losing. It wasn't just military defeats. It was an economic mismatch that could never be overcome." The Norden bomb site itself, as a device, was not the decisive weapon that American propaganda claimed. The Germans were correct that its effectiveness was reduced in combat conditions, that clouds and smoke and evasive maneuvering limited its precision. The strategic bombing campaign's actual effectiveness in reducing German production remained a subject of historical debate for decades after the war. Some economists argued that German production actually increased in 1944 despite the bombing, suggesting the campaign failed its primary objective. But the Norden's true impact was never purely military. It was psychological and symbolic. To the American public, it represented the marriage of American ingenuity and industrial might. To the crews, who used it, it provided confidence that their missions had purpose, that they were conducting precision strikes rather than terror bombing. To neutral observers, it demonstrated that American claims about technical prowess were not mere propaganda. And to the German engineers who evaluated it in that cold hangar in February of 1943, it revealed an uncomfortable truth about the war's inevitable trajectory. The technical specifications of the Norden have been declassified for decades now. its mechanical secrets no longer valuable in an age of laser-guided munitions and GPS navigation. But the story of its evaluation at Rechlin-Laerts endures as an example of how technology reveals not just tactical advantages but strategic realities. The engineers examining the device were not just assessing a bomb site. They were confronting evidence of an industrial system that could afford complexity, that could manufacture precision at scale, that could lose bombers by the dozen and replace them faster than Germany could shoot them down. Botz survived the war and worked in the German aerospace industry during Reconstruction, contributing to civil aviation projects. He rarely spoke publicly about his wartime service, but in private conversations with colleagues, he would sometimes mention the Norden evaluation. "We were good engineers," he would say, "but they had better resources. In the end, that mattered more than cleverness." The lesson of the Norden bomb site was not about the superiority of American engineering genius over German technical expertise. Both nations produced brilliant engineers and innovative designs throughout the war. The lesson was about economic systems and industrial capacity, about the advantage that vast resources and mass production provide, even when individual craftsmanship might favor the opponent. Germany could build technically sophisticated weapons, but America could build sophisticated weapons in overwhelming quantities, and in modern warfare, quantity has a quality all its own. The captured device that arrived at Rechlin-Laerts in February of 1943 was 20 pounds of aluminum and glass, 2,000 moving parts arranged in precise mechanical harmony. But it carried information far heavier than its physical weight. Evidence of an industrial capacity that could equip hundreds of bombers with devices costing thousands of dollars each, that could absorb losses that would have crippled smaller nations, that could wage war at a scale that made traditional military calculations obsolete. The German engineers who tested the Norden bomb site discovered what their commanders were increasingly reluctant to acknowledge. That technological sophistication without economic depth was insufficient. That tactical brilliance could not overcome strategic material disadvantage. That a war between industrial systems would be won by the side with greater productive capacity, regardless of individual technical achievements. They had been asked to evaluate a bomb site, and in doing so, they had inadvertently evaluated the war itself. The technical evaluation at Rechlin-Laerts had been completed by April of 1943, but its implications continued reverberating through German military planning for the remainder of the war. The Norden bomb site analysis coincided with a period of escalating crisis in the Luftwaffe's defensive capabilities. The Americans were not just bombing with greater precision, they were bombing with greater frequency, deeper penetration, and in formations that German fighter tactics had not been designed to counter. General Adolf Galland, commander of German fighter forces, received Botz's report with grim resignation. Galland was one of the Luftwaffe's most capable tacticians, a veteran of the Spanish Civil War and the Battle of Britain, with combat experience that informed his strategic thinking. Unlike some of his colleagues who dismissed inconvenient intelligence, Galland understood immediately what the Norden evaluation meant for air defense doctrine. If the Americans could maintain formation discipline under fire and achieve bombing accuracy that destroyed specific industrial targets, then the entire German strategy of dispersing war production across multiple sites would prove inadequate. The math was brutal. A single B-17 formation of 18 aircraft, each carrying approximately 4,000 pounds of bombs, could deliver 72,000 pounds of ordnance onto a target area measuring roughly 500 yards in diameter. With Norden-assisted accuracy, this meant that a factory complex could be systematically destroyed in a single raid, requiring perhaps 3 or 4 formations hitting different sections of the facility. To prevent this, German fighters needed to disrupt the formations before they reached the target, forcing individual bombers to break formation and conduct independent bombing runs that would scatter their ordnance across a much wider area. But disrupting B-17 formations was proving extraordinarily difficult. The Americans flew in combat box formations designed specifically to maximize defensive firepower. Each B-17 carried 13 50 caliber machine guns, and in a proper formation, the overlapping fields of fire meant that attacking fighters faced concentrated defensive barrages from multiple aircraft simultaneously. German fighter pilots reported that approaching a B-17 formation was like flying into a cloud of steel, with tracer rounds creating visible webs of intersecting fire. Gallen's response to the Norden evaluation was to intensify development of heavy weapons that could destroy bombers from beyond the range of their defensive guns. The Werfer Granit 21, a large-caliber rocket mounted under fighter wings, began deployment in summer of 1943. The Mk 108 30mm cannon, capable of destroying a B-17 with just 4 hits, entered production. These
were desperate innovations, attempts to offset American material advantage with tactical ingenuity. They had some success, particularly during the Second Schweinfurt raid in October of 1943, when German fighters shot down 60 B-17s in a single day. But even that devastating tactical victory revealed the strategic problem. 60 bombers destroyed represented perhaps 2 weeks of American production. The 8th Air Force losses were replaced within a month, while the German fighters and pilots lost in the engagement took much longer to replace. The attrition equation favored the Americans, who could afford to trade aircraft and crews at rates that would have bankrupted Germany's more limited industrial capacity. The engineers at Recklinghierz, meanwhile, had moved on to evaluating other captured Allied technology. In May of 1943, they received a damaged H-2X radar bombing system from a downed B-17, a device that allowed bombing through clouds using radar targeting. This technology was even more disturbing than the Norden because it eliminated the bomb site's primary weakness, the requirement for visual target identification. With H-2X, American bombers could conduct precision raids in weather conditions that would have grounded the Luftwaffe entirely. The psychological burden on German technical staff at facilities like Recklinghierz was immense and rarely acknowledged in historical accounts. These were professionals who had dedicated their careers to German aviation, who had contributed to designs like the Messerschmitt Bf-109 and the Focke-Wulf FW-190, aircraft that in many respects matched or exceeded Allied fighters in performance. They were not incompetent, nor were they working with primitive tools. German aviation technology in 1939 had been world-leading, the product of a systematic rearmament program that had begun in secret during the 1920s. But by 1943, they were confronting a different kind of challenge. It wasn't that individual Allied technologies were necessarily superior to German equivalents. The Luftwaffe had effective bomb sites, capable radar systems, and innovative weapons. The problem was scale. Every captured Allied device revealed the same underlying truth. The Americans could afford redundancy, complexity, and high unit costs, because their industrial capacity operated at levels that made such expenses trivial. Consider the production numbers. In 1943, the United States manufactured approximately 85,000 aircraft. Germany, despite heroic efforts to maximize production, built approximately 25,000 aircraft the same year. The American figure included thousands of heavy bombers, each one a complex 4-engine aircraft, requiring hundreds of thousands of man-hours to construct. Germany had largely abandoned heavy bomber production, focusing instead on fighters and tactical bombers that consumed fewer resources per unit. The Norden bomb sight was expensive, but each B-17 cost approximately $200,000 to build, meaning the bomb sight represented just 4% of the aircraft's total cost. Germany couldn't afford to build B-17 equivalents in meaningful numbers, so the question of whether to install expensive bomb sites was irrelevant. The entire strategic bombing capability that the Norden enabled was beyond German economic reach by 1943. Batz and his colleagues at Rechlin-Laerts documented these disparities in technical reports that became increasingly philosophical in tone. A June 1943 analysis noted that Allied technical philosophy appears to prioritize overwhelming force application over elegant efficiency. While German engineering seeks optimal performance within resource constraints, American engineering assumes effectively unlimited resources and designs accordingly. This fundamental difference in design philosophy creates systems we cannot easily counter because they operate outside our conceptual framework. This was as close as German military documentation came to acknowledging that the war was being lost, not on battlefields, but in factories, not through tactical errors, but through economic fundamentals. The Norden bomb site had become a symbol for this larger reality, a physical object that crystallized abstract economic disparities into something tangible that engineers could hold and measure. The summer of 1943 saw the evaluation team at Rechlin-Laerts expand their analysis to include captured American manufacturing documentation. When B-17s were shot down, they often carried not just equipment, but paperwork, maintenance manuals, parts catalogs, production schedules. This documentation proved as revealing as the hardware itself. The maintenance manuals assumed parts availability that seemed fantastical to German logistics officers accustomed to chronic shortages. Replacement bomb site components were listed as standard inventory items, available through normal supply channels, with delivery times measured in days rather than months. One captured document, a parts requisition form from the 91st Bomb Group, listed 17 different items, including replacement gyroscopes for Norden bomb sites. The form was dated, approved, and noted fulfilled within 6 days. A comparable German requisition for specialized optical equipment would have required weeks of processing, multiple authorization levels, and likely resulted in a response explaining that the parts were unavailable and improvisation was necessary. This bureaucratic evidence reinforced what the technical analysis had suggested. American logistics operated at a level of abundance that made rapid replacement of complex components routine. A damaged Norden bomb site didn't ground a bomber for months. It was simply swapped out for a replacement unit, with the damaged original returned to depot-level maintenance for repair or salvage. This approach required maintaining enormous inventories of spare parts, a luxury possible only with massive industrial overcapacity. German logistics, by contrast, operated on principles of scarcity management. Parts were conserved, components were repaired and reused until failure, and improvisation was not just encouraged, but necessary. Luftwaffe ground crews became expert at cannibalizing damaged aircraft to keep operational ones flying, at jury-rigging repairs with non-standard parts, at extracting maximum service life from equipment designed for replacement. These were admirable skills born of necessity, but they absorbed time and expertise that the Americans devoted to simply installing new components. The Rechlin-Laerts team's analysis expanded beyond the Norden itself to examine the entire bombing system that made its precision possible. The bomb site was one component in a complex of technologies that included aircraft design, formation tactics, navigation systems, and target identification procedures. Each element reinforced the others, creating a synergistic capability that exceeded the sum of individual parts. For example, the B-17's turbocharged engines enabled operations at altitudes where German fighters suffered performance degradation. This altitude advantage provided more time for the Norden's calculations during bomb release, as bombs falling from 25,000 feet had longer trajectories that the bomb site could more accurately predict.
The defensive armament allowed formations to maintain cohesion under attack, which kept individual bombers in proper position for their bombing runs. The advanced radio navigation systems enabled precise formation assembly and target approach, ensuring bombardiers had adequate time to set up the Norden for optimal accuracy. Examining this integrated system, the German engineers realized they were not looking at a device but at a doctrine, a comprehensive approach to strategic bombing that required technological capability, industrial capacity, and tactical coordination operating in perfect synchronization. Germany could potentially copy any single element, but replicating the entire system was impossible because it required resources Germany simply did not possess. This realization led to a series of recommendations from Rechlin-Laerz that were largely ignored by Luftwaffe command. Botz and his team suggested that rather than attempting to match American bombing capabilities, Germany should focus on developing countermeasures that exploited the Norden's known weaknesses. Smoke generators could obscure targets, reducing visual bombing accuracy. Electronic jamming might disrupt the radar bombing systems that supplemented the Norden in poor weather. Fighter tactics should prioritize formation disruption rather than individual bomber destruction, accepting lower kill ratios in exchange for degrading bombing accuracy. Some of these recommendations were implemented, particularly the increased use of smoke screens over critical targets. But the fundamental problem remained. Any effective countermeasure required resources, and resources were increasingly scarce as Allied bombing systematically destroyed German production capacity. The Luftwaffe needed more fighters, better pilots, more fuel, improved radar, additional anti-aircraft guns, and more effective communication systems. All of these competed for limited industrial output while also requiring the very factories that Allied bombers were destroying. The vicious cycle was apparent to the engineers at Rechlin-Laerz, even if it remained officially unacknowledged. Every successful American raid reduced German productive capacity, which reduced the ability to build countermeasures which enabled more successful raids. The Norden bomb sight, with its precision targeting, accelerated this cycle by ensuring that bombs hit the facilities that mattered most: ball-bearing factories, oil refineries, aircraft plants, transportation hubs. By late 1943, the tone of Rechlin-Laerz reports had shifted from technical assessment to something approaching elegy. A November analysis of captured American aircraft components noted that the material quality and manufacturing precision evident in Allied equipment suggests an industrial capability operating with minimal resource constraints. Components show no evidence of material substitution or simplified manufacturing processes, indicating that supply limitations are not affecting production standards. This was engineering language for a devastating conclusion. While Germany was desperately substituting inferior materials to maintain production, while factories were simplifying designs to reduce manufacturing complexity, while quality control was being relaxed to meet quantity demands, the Americans were building equipment to peacetime standards. They could afford to maintain precision, to use optimal materials, to include redundant safety features. The economic disparity was so vast that it affected even the microscopic details of manufacturing. The human cost of this realization fell hardest on the engineers and technicians who understood its implications. Several accounts from Rechlin-Laerz personnel describe a pervasive sense of professional despair during the final years of the war. They continued their work because duty and professionalism demanded it, but the conviction that their efforts mattered had eroded. They were documenting Germany's technological inadequacy in meticulous detail, producing reports that accumulated in filing cabinets while the strategic situation deteriorated regardless of their recommendations. Botz himself exemplified this psychological trajectory. His early war reports had been confident, sometimes dismissive of Allied capabilities. His assessment of early British bombing raids in 1940 had noted their primitive accuracy and wasteful ordnance expenditure. But by 1944, his writing had acquired a different character, precise, thorough, and quietly fatalistic. He documented Allied technological advances with the detachment of a pathologist performing an autopsy, describing in clinical detail the mechanisms by which German air defenses were being systematically overwhelmed. The final irony of the Norden bombsight story emerged only after the war, when American post-war assessments revealed that the device's actual combat effectiveness had been significantly less than claimed. The United States Strategic Bombing Survey, conducted in 1945 and 46, determined that only about 20% of American bombs fell within 1,000 feet of their aim points, despite the Norden's theoretical precision. Weather, smoke, combat stress, equipment malfunctions, and human error reduced the device's practical accuracy far below its technical capabilities. This finding might have vindicated the German engineers' skepticism about American publicity claims, except that 20% accuracy was still devastatingly effective. It meant that 1 in 5 bombs hit close enough to the target to cause significant damage, and with the volume of ordnance American bombers delivered, this ratio was sufficient to systematically destroy German industrial capacity. Strategic bombing worked not because every bomb hit its target, but because enough bombs hit enough targets frequently enough to overwhelm repair and reconstruction efforts. The German engineers at Recklinck-Larz had been correct that the Norden could not achieve its advertised pickle-barrel precision in combat, but they had underestimated the degree to which approximate accuracy, delivered at overwhelming scale, would prove strategically decisive. The bombsight didn't need to be perfect. It just needed to be good enough, and when combined with unlimited productive capacity, good enough was sufficient. This perhaps was the deepest lesson of the Norden evaluation, that in industrial warfare, adequacy at scale defeats perfection in scarcity. German engineering had pursued elegant solutions optimized for resource-constrained environments. American engineering had pursued robust solutions assuming resource abundance. The difference in philosophy reflected different economic realities, and those economic realities ultimately determined the war's outcome more surely than any single battle or campaign. The captured Norden bomb site that arrived at Recklinck-Larz in February of 1943 was just one device among thousands in service with the 8th Air Force. Its evaluation changed nothing strategically. The bombing campaign continued regardless of whether German engineers understood the technology enabling it. But for the men who examined it, who disassembled its components and tested its capabilities and documented its sophistication, the experience provided a clarity that was both intellectually satisfying and emotionally devastating. They had been asked to evaluate enemy technology, and had discovered instead a mirror reflecting Germany's industrial inadequacy. They had approached the task as engineers solving a technical problem, and found themselves confronting an economic reality that no amount of engineering cleverness could overcome. They had measured the precision of a bomb site and calculated with unwanted accuracy the trajectory of the war itself. In the decades after the war, as American and German engineers sometimes worked together in projects like NATO defense programs and European aerospace development, the Recklinck-Larz veterans occasionally shared their wartime experiences. The Norden evaluation was remembered not as a moment of discovery, but as a moment of recognition, when abstract knowledge about American industrial capacity became concrete understanding through the medium of a physical device. They had held in their hands the evidence of their nation's coming defeat, wrapped in aluminum housing and mounted on a gyroscopic platform, computing trajectories with mathematical indifference to human hopes or national pride. The Norden bomb site itself has become a museum artifact now. Examples preserved in aviation collections from the Smithsonian to the Imperial War Museum. Visitors can examine the intricate mechanism, read the technical specifications, and marvel at the analog computing achievement it represented in the pre-digital age. But the device's true historical significance lies not in its technical specifications, but in what it revealed to those who studied it during the war. That technological sophistication without economic depth is insufficient. That material abundance enables capabilities that tactical brilliance cannot counter. That wars between industrial powers are ultimately won in factories rather than on battlefields. The German engineers at Rechlin-Laerts had tested a captured American bomb site and discovered why B-17 formations kept coming back, why German cities kept burning, why the industrial capacity supporting the Wehrmacht kept shrinking despite heroic defensive efforts. They discovered that precision bombing, even imperfect precision, was accurate enough when delivered at American scale. They discovered that the pickle barrel claims were propaganda, but that propaganda based on partial truth is often more effective than pure fabrication. Most significantly, they discovered that understanding why you are losing does not provide the means to prevent the loss when the causes are economic fundamentals beyond tactical correction. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.